Welcome to The Explainer. Today, we're taking a little tour of a really fascinating neighborhood on the periodic table, the P block. This is home to groups 16, 17, and 18, and we're talking about some heavy hitters here, from the oxygen we need to live, to the halogens that light up our world, and even those famously standoffish noble gases. So here's our game plan. First, we'll get properly introduced to our P-block neighbors and figure out what makes them all part of the same club. Then we'll dive into the super predictable traits that run in these families. After that, we'll meet the oddballs, the firstborn elements that just love to break the rules. Then things get wild when we see what happens when halogens mix with each other, and we'll wrap it all up with a huge surprise from the noble gases. All right, first up, let's meet the residents of this neighborhood. We need to lay the foundation and understand the fundamental chemistry that really makes them tick. So what is it that ties all these different elements together? Well, it's actually pretty simple. It all comes down to where their very last electron goes. For every single element in groups 13 through 18, that final electron finds its home in what's called a p orbital. And believe it or not, that one little fact is the key to pretty much everything they do. And that's why we always start with their electron configurations. You have to think of them like chemical blueprints. They tell us exactly how these elements are going to behave, what they look like, and the kinds of bonds they can form. Now check this out. Look how incredibly close groups 16 and 17 are to having that perfect full outer shell, just like the noble gases. The oxygen family, they're just 2 electrons away, and the halogens, they're only 1 electron short. This makes them, well, kind of desperate to grab electrons, and that's exactly what makes them so incredibly reactive. Okay, so those electron blueprints we just talked about, they lead to some really predictable family traits. As we move down each of these groups, these clear, consistent patterns just start to pop out. So, here's the first big trend. As you take a step down a group, say from oxygen to sulfur, you're adding a whole new shell of electrons. It's kind of like adding another layer to an onion, right? So it just makes sense that the atoms get bigger and bigger and bigger as you go down the column. And you can totally see this in the numbers for group 16. Oxygen at the top is pretty tiny, just 66 picometers. But by the time you get all the way down to polonium, it's more than doubled in size. The pattern holds up perfectly. This one makes perfect sense once you get the size thing. In a really big atom, that outermost electron is way, way out there, far from the positive pole of the nucleus. It's just not held on as tightly, so it takes a lot less energy to just pluck it away. And the exact same logic applies to electronegativity, which is all about attracting electrons. Smaller atoms with their positive nucleus closer to the action have a much stronger pull on any electrons passing by. It's no surprise then that fluorine, sitting right at the top of group 17, is the most electron-greedy element there is. But, just like in any family, the trends aren't always perfect. The firstborn members of these groups, I'm looking at you, oxygen and fluorine, they're a little bit weird. They don't always play by the rules set by their heavier siblings down the group. So let's take fluorine. Why is it such an outlier? Well, it boils down to 4 main things. It's super small and incredibly electronegative, which we'd expect. But it's also missing these things called d orbitals, which gives other elements more flexibility in bonding. And here's the real kicker. The bond holding 2 fluorine atoms together is surprisingly weak, which means it's super easy for it to break apart and cause some chemical chaos. And this slide really shows just how different fluorine is. My favorite example is its compound with hydrogen. Hydrogen chloride, hydrogen bromide, all gases at room temperature. But hydrogen fluoride, it's a liquid. Why? Well, because fluorine is so tiny and intensely electronegative, it forms these super strong attractions between molecules called hydrogen bonds, something its bigger siblings just can't pull off. It's a total game changer. Okay, so this is where things get really fun. What happens when the halogens, the super reactive bunch from group 17, don't just react with other elements, but with each other? It seems like a weird question, right? I mean, why would these elements who are all desperate to gain an electron react with each other? Well, the answer opens up a whole new, fascinating class of compounds. It works because even within the halogen family, they have different sizes and electronegativities. So one halogen can sort of act as the more positive center, while another, more electron-hungry halogen bonds to it. And voila, you get what we call an interhalogen compound. And they come in 4 main flavors, all following a pretty simple recipe. The X is always the bigger, less electronegative halogen, and the X prime is the smaller, more aggressive one. The bigger the size difference between them, the more of those little atoms you can pack around the central one. And the result of all this is that these compounds form some truly bizarre 3D shapes. I mean, to make room for all the electrons flying around, they have to twist themselves into geometries you don't see every day, like this bent T-shape or even a square pyramidal structure. It's pretty wild stuff. All right, and now for the biggest surprise on our tour, the final plot twist. And it comes from the most reclusive, standoffish family in the entire neighborhood, the noble gases over in Group 18. For decades, literally decades, the answer from every chemist in the world was a hard yes. They have perfectly stable, completely filled electron shells. They have zero reason to react with anything. They were the gold standard of chemical stability, completely inert. But that all got turned on its head in 1962. A chemist, Neil Bartlett, had just made a powerful compound that was strong enough to steal an electron from an oxygen molecule. And then he had this brilliant thought. He knew the energy it takes to steal an electron from a xenon atom was about the same as from oxygen. So he thought, wait a minute, maybe, just maybe, his compound could react with xenon too. And you know what? He was right. And this was it. This was the groundbreaking result. Under the right conditions, xenon, a supposedly unreactive noble gas, reacted directly with fluorine to create a stable, solid compound. The chemistry textbooks literally had to be rewritten. A whole new field of science was born overnight. And it wasn't just a one-off fluke. It was like opening the floodgates. Suddenly, scientists discovered that this inert element could actually form a whole family of stable compounds. Mostly when it was forced to react with the most aggressive elements out there, fluorine and oxygen. So this little tour through the P block really shows us something important. The periodic table isn't just some static chart of facts you have to memorize. It's a dynamic map of incredible and sometimes completely shocking chemical potential. It really makes you wonder, doesn't it? What other unbreakable rule in science is just waiting for the right experiment to come along and shatter it?